So first of all, on the class webpage, I stated clearly the homework problem. And also, I've really postponed it to Thursday, so if you get it in early, great. If not, remember, send it to Mr. Yu and or put it in his box. I don't know if I mentioned this last time, but I was watching a Kip Thorne colloquium over the internet, and one of the things he mentioned is that Newton's laws set the stage for physics for 200 years. And now Einstein has set the stage for physics for already 100 years. And that surprised me because I always had imagined that the era of Newton was semi-infinite and that Einstein was recent. In fact, I was alive when Einstein died in 1955. The lesson from that, I think, is that there are two lessons. One is that we've been really ignoring Einstein. We adopted special relativity because it was simple, but general relativity hasn't really permeated physics enough. And the second thing is that it's high time that we integrated general relativity with quantum mechanics. As I mentioned to you, quantum field theory is basically built from very few assumptions. One is special relativity, one is quantum mechanics. And that's about, the third is the concept of a field. That is to say, the field should play a key role. And then the fourth thing is something that artists know about, namely that you should try that sometimes less is more. In other words, if you put in all possible details, many of the details distract. And in the case of physics, if you put in too much, some of the things you put in are wrong. And so in quantum field theory, it's really a theory of we talk about it as particle physics, but we completely leave out the particles. The particles aren't described at all. We describe the fields that create and annihilate the particles. We say the particles have momentum and spin. We don't say anything about what their internal structure might be and so forth. So the success of quantum field theory is partly because it did not attempt things that we still can't do. And now, though it's 100 years after Einstein, it's about time maybe we try to do those things. I'm not going to try to do them in this course, but you guys are young, maybe you can do it. Another thing, well, actually, I should start lecturing about the normal course, but I'll just make one other remark. I was watching another video more recently of a guy at Cornell named something like Tukowski, and he is describing the successes of the gravitational wave experiments, and this is really important stuff. Already, with just a couple of years of observations, or actual observations, they've enormously lowered the upper limit on the mass of the graviton. I forget the number he gave, but it was better than 10 to the minus 15 electron volts. Might have been 10 to the minus 20 electron volts. Very small. And of course, that's again of a piece with this business that we should be paying more attention to Einstein. Or I'm going beyond Einstein. All right, so let me get to what I actually meant to talk about, if I get my notes straight here. I think these and these are the right ones. Okay. So last week we reviewed the structure of the rotation group and the Lorentz group, and now it's time to think a little bit about. So let me just get my notation straight here. So L is a Lorentz transformation, and in particular, the Lorentz transformations are characterized by the 4x4 matrices. L transpose eta L is eta, and L inverse is eta L transpose eta. Anyway, U inverse of L on, say, pi U of L. Pi is the momentum operator. This is L, let us say, Ki pi. And so momentum operator changes by that much. And let's think about a state of momentum P. So PA on a state of momentum P in spin sigma versus PA P in sigma. So I'm basically going to be translating and trying to simplify Weinberg's chapter 2 here. And in particular, PA U of L on P and sigma, well, we can say that this is U of L PA, sorry, U of L, let me read my own notes, hold on. U inverse of L PA, U of L P sigma. So this is U of L. This structure here is, well, we can call this LP. So this is LP, or LA, let's see, if it's IA, PA, P in sigma, and this is LIA, PA, U of L, P sigma. So what this simple derivation tells you is that the momentum operator, or the energy momentum operator, on the unitary operator corresponding to a Lorentz transformation L, acting on the state of momentum P and Z component of spin here, or let us say, let us just call it sigma for the moment. We haven't gone that far. That's the transformed, the Lorentz transformed momentum times U of L on P sigma. So this is telling us that right. So this is telling us that U of L on P sigma is some linear combination of the states LP. So in other words, this is telling us that the unitary transformation corresponding to Lorentz transformation on the state P sigma is a linear combination of states with momentum LP. LP being this here. And so the next step is to systematize this, and what Weinberg does is choose a standard momentum K. And if you have a massive particle, then this is M000. If you have a massless particle, then this, I'm going to choose it as 1100. He chooses it as 1001, and I found that I think that's a little more confusing, so I'm going to choose it this way. In fact, he doesn't play with the matrices very much at all. And then we're going to have a standard Lorentz transformation, LP, that will take us from K to P. So in other words, if we're talking about a state of momentum P, we're going to think in terms of standard fiducial for momentum, a standard Lorentz transformation that takes us from the standard fiducial 4-vector to the 4-vector P. And that's just to systematize things and to figure out what's what. And in particular, then, we'll be able to define a state P sigma as being some normalization factor, a unitary transformation associated with L of P on a state K sigma. And in particular, we're going to keep these sigmas the same. So this is just the way Weinberg sets up quantum mechanics and special relativity. Most quantum field theory treatments just skip over this and let the reader figure it out, or just forget about it. Okay, the next point is.
Wait, so can I ask a question about like the choice of the fiducial state?
Give me that again.
Like your choice of fiducial state. How would you choose such a fiducial state?
Why would we
like
choose that?
Or no. I'm just saying like what would determine what you choose? Like, could I just use?
Oh, simplicity.
basis
Simplicity.
Okay, so I imagine what like the simplest choice might just be to use like standard basis vectors in a 4-dimensional space, or I mean, why do you like 1100? Like your choice.
Well.
What makes
Well,
your
first of
choice?
all, this is the massive case.
Okay.
I forgot to mention,
okay.
This is the massless case.
Okay.
And,
So
as
you
far
only
as we
have one
know, the photon
fiducial
and the
state.
graviton are both massless.
Okay.
And the gluons are believed to be
Yeah.
massless. So what?
So your idea is to create a state with momentum P. You start out in some reference frame where the thing isn't moving, like in the massive case. You have something with
Right,
mass,
right,
it
except
isn't
for m
moving,
equals
and then
0,
you
it's always
Lorentz
moving.
boost into,
Yeah.
Yeah, I see.
Yeah, this is the way he sets up and explains how it is that the particles transform, and then how it is that fields transform. Okay, so now that we've set up the states, what happens if we act on the states with an arbitrary, whoops, once again, I made a mistake. An arbitrary Lorentz transformation, so I'm going to use a Greek letter lambda. I think that I try to suppress the use of Greek because most of us aren't Greek, and every time we see some Greek symbol that uses a whole bunch of neurons that we don't normally use, and I think that just confuses everybody. So what is this? Well, it's the normalization factor for this state. Then it's u of lambda. And then we said that state was L of P on the state K sigma. So that's the way Weinberg has set it up. And so then this is N of P. These things are unitary matrices, and they form a unitary representation of the Lorentz group. Notice that it's an infinite dimensional representation, because finite dimensional representations of non-compact groups can't be unitary. Anyway, so this is lambda L of P, K sigma. And now there's a standard thing that is done. Once again, it was done by Wigner and Weinberg, who was a graduate student at Princeton, picked it up from Wigner. Namely, we rewrite things in an interesting way. We write this as U of L of lambda P. So this is the standard Lorentz transformation that takes one from K to the vector lambda P. And the next step is U of L inverse of lambda P, and then U of lambda L of P, and then K sigma. Now we rewrite this as NP U of L of lambda P. Now we again take into account that this is a unitary representation of the Lorentz group, and so this is really U of L inverse of lambda P, lambda L of P. And I think I need another parenthesis there, and then this is K sigma. Okay. Now, there's something interesting about this particular combination. It's named after Wigner. If we write it out, it's L inverse of lambda P, lambda L of P. Let me write this a little more clearly. Okay. Now, the interesting thing about this is that this is called, all right, let me just go a little bit further. Let us operate on our standard vector m0 for a massive particle and 1, 1, 0, 0 for a massless particle. Well, this is L inverse lambda P, lambda, but now L of pk, well, L of pk is just P. So this is L inverse of lambda P, lambda P. But on the other hand, this is the Lorentz transformation that takes one, well, without the inverse, this is the Lorentz transformation that takes one from K to lambda P. So the inverse of that takes one from lambda P back to K. So this is K. So in other words, this W of lambda and P on K is K. And this is true whether we're in the massless or the massive case. In the massive case, we know what these things are. Yes?
I don't quite understand the last step. So how it gets equals to K? How's it get that equals to K?
Okay. This 4-vector, lambda P, well, here, L of lambda p takes k to lambda p. So L inverse of lambda p takes lambda p to k.
Where we got the first relation? I'm sorry, the first equation where we got that? Where we get the first equation?
I mean, where did we get this?
Yes.
Okay, good, great question.
That's it.
But in view of the shortage, I can't give you another one. L of p is defined by this. So for any p, L of p is a, I'll say what it is later, but at the moment it's simply a chosen Lorentz transformation that takes us from the standard 4-vector to the 4-vector p. Now there's more than one way of doing that. We'll pick a standard way in a little while. In fact, what I'm amazed at is that I've covered so much material in just 20 minutes. I'm going to run out of things to say today, I'm afraid. I think we should call it an early day. Okay, so in the Massless case, then, this is a Lorentz transformation that leaves k invariant. K is M0, so this is clearly a rotation. So this thing is actually called a Wigner rotation. In the massless case, it's something else. And we'll find out what that is later today. It's of course the group of Lorentz transformations that leave the standard fiducial vector invariant. And in this case, it's 4 vectors that represent particles of energy 1 and momentum 1 moving in the x direction. And clearly rotations about the x-axis are part of the little group of this massless standard vector. By the way, these W's then are they're Lorentz transformations that leave k invariant, consequently they form a group. Because if one, that's just the nature of, they form a subgroup of the Lorentz group or a group by themselves. And it's called, nicely enough, it's called the little group. Very often in physics, people have used extravagant names. And it's sometimes charming when somebody uses a name that's appropriate and unspectacular, like little. Anyway, it's the little group. So you have the Lorentz group, then you have this little group. And in fact, I think one of the reasons why Congress canceled the SSC, which would have been a very good machine, is that it was called the superconducting super collider. The use of the word super twice, once was bad, twice was absurd. And in Congress you have many people who are lawyers. Lawyers are very sensitive to language, and they know stupid writing when they see it. And I think that's part of the reason it went down. Main reason, of course, is that we don't care about, as our current president has shown, as a country, we don't care about anything intellectual. By the way, I hope you're all registered to vote. And I hope all your friends are registered to vote. And I hope that you drag them all to the polls in November. Because as Paul Krugman wrote yesterday in the New York Times. We're not that far from following Poland and Austria into a kind of early fascism. And, we think it happened in Germany, there's something wrong with the Germans. No, Germans are human. It happened in Germany, it can happen here. And, so, go to the polls and vote in November with all your friends. So this is called the little group. And once again, the little group is such that WK is K. Massless particles, this is K. Massive particles, that's K. Okay, now what is this little group like? Well, suppose we have U of W on some K sigma. So this is a state that represents a particle that has a fiducial momentum. And this is evidently a sum, sigma prime, of some d of sigma prime sigma of W times K sigma prime. So it leaves the momentum K invariant, so full momentum K invariant, so it must be a linear combination of these states. And we can then think about this. What about some sigma prime, d sigma prime sigma of W prime W? So this is two Wigner rotations, although in general, for the massless case, they're not rotations. Well, they could be rotations, they're not always rotations. So this is causes U of W prime W, K sigma. And it's also U of W prime, U of, oops. U of W on K sigma. And so this is U of W prime. Some sigma double prime, d sigma double prime sigma of W, K sigma double prime, and so that's some sigma double prime. I'm just rewriting this for clarity. So this has to be some sigma double prime, d sigma double prime sigma of W. And now this one is some sigma prime, d sigma prime, sigma double prime of W prime. Now this is K sigma prime. Hey, you guys, you were supposed to tell me to turn this off, because it does very little good, but makes so much noise that the audio gets hard to follow. So now if we compare this line with that line, what we see is that these W's, these D's form a group. In other words, some sigma prime, D sigma prime, sigma, or to put it more simply, what we found is that D sigma prime sigma of W prime W is some sigma double prime, D sigma double prime sigma of W. Let me get the right, yeah, that's probably right. D sigma prime, sigma double prime W prime, I've got the wrong, this is actually, well, let me just say that if I had gotten everything straight, this would have been it. And if I might write this a little bit more nicely, it looks like this. Okay, so this means, so in matrix notation, this is just saying D of W prime W is equal to D of W prime D of W. So these D's are representations of the little group, which is, of course, what we expect. So in other words, when U of W acts on K sigma, we get a representation of the little group acting on K sigma. And if we now go back to the original, the more general case of an arbitrary Lorentz transformation lambda on K sigma, let me just move this. This, as we said, was a normalization factor U of L of lambda P, U of L inverse of lambda P, lambda L of P, K sigma. And so this is N of P, U of L of lambda P, U of the Wigner rotation. I'm calling it Wigner rotation, but the massless case, it's not really a rotation. And now we know what this is because we've just basically worked that out. So this is N of P, U of L of lambda P, some sigma prime, D sigma sigma prime, W of lambda and P, K sigma prime. On the other hand, this one hits that, and so this is N of P, some sigma prime, D sigma sigma prime of W of lambda and P. Well, I'm just sort of rewriting this. L of lambda P on K sigma prime. And this is then N of P, some sigma prime, D sigma sigma prime of W of lambda and P. And this, by our definition, the way we set things up, is lambda P sigma prime. That just gives us this, apart from a normalization factor N of lambda P. So our overall equation, arbitrary Lorentz transformation, lambda, unitary operator representing the Lorentz transformation lambda, on P sigma is N of P over N of lambda P, some sigma prime, D sigma sigma prime, W of lambda and P. And then the state lambda P sigma prime and Now, there's the issue of normalization. One part that's kind of obvious is that we will want, since these represent momenta and these are spin directions, we expect this to be totally orthogonal, so delta sigma prime sigma, delta q, k minus k prime. And in fact, more generally, we're going to choose to normalize states in this way. We're going to say p prime p sigma is going to be simply delta q of p minus p prime delta sigma prime sigma. So that's the normalization. This is a choice of normalization. N of p is square root of k0 over p0. So that's we've finally chosen what this arbitrary N of p is. Okay, let's see. I think I'm going to tell you a brief story because I've gone through an awful lot of material in 35 minutes. It's something I learned on the BBC today, or yesterday or the day before, a couple of days ago, over the weekend. Back in the period 1913 to 1916, the Russian government, under the Tsar, decided that alcoholism in Russia was a serious problem. And not only decided it, was decided to do something about it. I don't know what they did, but they raised taxes on alcohol, made it more difficult to buy alcohol, and so on and so forth. That caused severe civil unrest. And it was one of the reasons for the Russian Revolution of 1917. One of the main reasons. Flash forward, 1991, Gorbachev realized that alcoholism was still a problem in the Soviet Union, tried to do something about alcoholism in the Soviet Union. And I know a little bit about what he did. He raised taxes on alcohol. And he said that you could only buy a liter of vodka per day, per person. And so you'd need more than a liter. But then, I don't know, there were other rules that he introduced. Caused severe civil unrest, and it was one of the major reasons for the collapse of the Soviet Union in a few months later, 1991. So I think that's very amusing, and I thought it would be a nice break.
Little note in addition to that, whether it's true or not.
Well, this is true.
Whether it's true now or not, for a long time, Moscow had the highest rate of alcohol poisoning deaths in the world.
Yeah.
Just a little something I read.
And of course, the reason is that people in Moscow could afford to buy more vodka than people in the country. Yeah.
I'm saying trouble reading that. Is that K superscript 0, P superscript 0, it's NP? Or what, I can't, what's after the P? Right here. No.
That's a prime.
No, right here. So
That's
is
a
that
K0.
So K superscript 0, and what's this?
P superscript 0.
Okay.
This is just, in other words,
Yeah.
square root of E of K divided by E of P.
What are the...
So you get a candy. Hold on. And what's your question?
I'm sorry, Professor, can you explain what is U, lambda, and air?
Explain what?
What is U, lambda, and air?
What is U?
Yeah, sorry.
What is U?
Lambda, and air.
First of all, lambda is just an arbitrary Lorentz transformation.
Okay.
So you can think of it as a 4x4 matrix, satisfying the conditions in the upper left chord. U is a unitary operator that represents this Lorentz transformation.
Okay.
And so as a unitary operator, you can think of it as an infinite dimensional matrix.
What about air?
Hmm?
What about air? What about air?
Air?
L.
Air.
What about L? L is a special Lorentz transformation, a standard Lorentz transformation. And in particular, L of pk is the standard Lorentz transformation that takes you from the standard fiducial 4-vector to 4-vector p. All right, so that's the end of the candy then. I will try to remember to buy one. No? You sure?
Wait, so if we defined L by this, so what does
Yes.
it mean to stick a lambda in the argument? That's kind of
Give me that again?
So we defined this L like P this way.
Yeah.
And then, so what does it mean to just stick a lambda in the argument?
Well, L of lambda p takes k to lambda p.
Okay.
Because lambda p is another 4-vector.
Oh, okay.
So L of lambda p is the standard Lorentz transformation that takes you from the standard fiducial vector to lambda p.
But
Weinberg
So another-
describes this in his chapter 2. Yeah?
yes, another question about that. Whenever you write L of p acting on k,
Whenever I write one?
yeah, whenever you say like L of p on k gives you p, do you really
L
mean?
of p on k gives you p, yes.
Yeah. Do you really mean whenever you say L of p on k? Do you really mean like the unitary representation?
No, no, no.
'Cause
Ellen,
these
no,
guys-
no, no. Let's be very. That's a great question.
Oh no, because k
This
is a 4
thing
vector.
is a 4
yeah,
by
I
4
see.
matrix.
Yeah.
This thing is a 4 vector.
Okay.
This thing is a 4 vector. So this is 4 by 4 matrix,
Okay.
fiducial 4 vector, arbitrary 4 vector. Arbitrary 4 by 4 matrix, arbitrary 4 vector, standard 4 by 4 Lorentz transformation, fiducial 4 vector gives you arbitrary 4 by 4 matrix multiplying 4 vector p, and that gives you another 4
I see.
vector.
So whenever you write like whenever you write a ket with p and sigma, what you really mean is it's like we've taken all these different p's
ket
and we
is
turned
the
them all
state.
into
The ket
okay.
Ket p
Oh, can I-
sigma
yeah.
is a state that has 4 momentum p and some other variables
Yeah.
that we haven't yet described later
Sure.
by
So
sigma.
every possible 4 momentum represents like an orthogonal vector in this like Hilbert space that you're talking about.
Give me that again, what?
Every possible 4 momentum that you could have represents an orthogonal vector in this Hilbert space. I mean that's what you wrote.
Well,
right?
yeah, but of course, let's be a little bit careful. The only physical momenta allowed are the ones that are given by L of p on k.
Yeah, sure.
So in particular, it's what happens when a Lorentz transformation hits M000
Yeah.
for massive case, and what happens when L hits 1100 for the massless case. These are the only 4 vectors that physical particles can have. Massless and massive, as far as we know.
Sure. And then, so, final question. What is K0?
You picked the wrong day to ask a lot of questions.
It's okay, I don't
Empty.
care about K. So what is K0 and P0 then? I mean, you read it as E of
Oh,
K.
K0
but I
and
don't
P0. Well, K0 in this case is
Yeah,
M.
okay.
K0 in this case is 1.
And what is P0?
And, well, P is a 4 vector. So it's P0, P1, P2, P3.
And it's what you get whenever you act L on K. Yeah.
Right, L of K gives you P.
Yeah, I see, okay. Makes sense.
So P is simply a 4 vector, K is a fiducial 4
Yeah.
vector.
Sorry, this may be stupid. What exactly do you mean by fiducial or vector?
Well, fiducial just means standard. And in particular, I chose 1100 for the Massless case. Weinberg uses 1001. And that's because he's smarter than I am and he can use anything he wants, whereas I use something simple. Okay, so for m greater than 0, what we have is that L of P, not L of P, N of P, this normalization thing is square root of m over P0. And U of L on the state P sigma is square root of lambda P 0 over P0 some sigma prime D. Now let me put here a J, sigma prime sigma. W, the Wigner rotation, lambda P that we defined earlier, the state lambda P, sigma prime, and now this sigma prime, we now know something about this. These things are just rotations, so these are representations of rotation group, and in quantum mechanics we learned all about that. Namely, they go from minus 2j plus 1 to 2j plus 1. So they're 2j plus 1 by 2j plus 1 dimensional square unitary matrices. Unitary because it's a rotation group, so it's compact. All right, let me move this out of the way. All right, that's the end of one set of notes. Let me get the other set. So let me just describe this one more time. For massive particles, K is that, dj, spin j, sigma prime sigma of theta. Now I'm going back to the stuff that I talked about last week. E to the minus I, theta dot j, where these j's are 2j plus 1 by 2j plus 1 matrices, and we have ji, jj, I, epsilon, ijk, jk, this is the rotation group, and j3, square matrix. These matrices are all square, sigma prime sigma, is sigma delta sigma prime sigma. So this is the J3 is diagonal, is the way we usually do it. Okay, so that's that. Get a little more light here. Get some light in here. Okay, now where am I in this? Okay, here. Okay, so yeah.
Questions about the generator here. I thought so. So are you saying this is a diagonal matrix, this J3 right here?
J3 we choose to make diagonal because state law requires that.
Yeah, but aren't they anti-symmetric? It's just one of the requirements you end up getting, so they can't have a diagonal term? I'm just kind of confused.
The Pauli.
So
Wait a minute.
SO3
Hold
has
on.
anti-symmetric
I don't know
generators.
what's anti-symmetric. The generators of the rotation group are like this. Ji, Jk's I, epsilon I, Jk, Jk. This thing is totally anti-symmetric.
No, I'm talking about, so the matrices, the generators of
These generators are Hermitian because it's the rotation group. And so that means they are real and symmetric. Or imaginary and anti-symmetric.
Okay. I was reading a book about this, and it was basically saying the generators of SO3 are just anti-symmetric matrices. So AT equals minus A. And that you can derive that directly from like
Well, you
the
can have
algebra.
ones that are, as I said, you could have them be
So, no, they'd be
imaginary
real.
and anti-symmetric.
No, but I'm saying they'd be real anti-symmetric. That's the thing this book is saying, basically. So it's saying they're real and anti-symmetric, or they're imaginary.
Well, Lord, let me rephrase it.
Okay.
If a matrix is real and square matrix is real and symmetric, it's Hermitian. If it's imaginary and anti-symmetric, it's Hermitian. It's possible to be Hermitian without being either one.
Okay, I think I know. Because when in the book I was talking about, they kind of don't have the I, because you can have the J's be real. So that's what I.
Yeah,
I'm sorry. I was
that's
talking
a book written by mathematicians, and I must say that the mathematicians, I think, use a nicer notation. I mean, I don't think we do ourselves any favors putting in I's and then canceling them.
Okay, yeah. So that. Okay, sorry.
Okay, so far I haven't said anything about what the standard Lorentz transformation is. The most convenient one, again for the massive case, so let me just write down here. I think this thing is wearing out. What we're going to do is we're going to think, well, I think I'm going to give up on this one. Let's see if this one's any better. That's the thing about these whiteboards, they're great if you just have pens. Okay, this one works. So LIK is delta IK plus gamma minus 1 P hat I, P hat K. By the way, in this notation, the first index is the row index, the second one is the column. So this is row, and this is column. Whether they're up or down has to do with these plus and minuses that occur in special relativity. And in general relativity, up or down is more sophisticated. It depends on whether you use the space-time metric to raise and lower indices. All right, anyway, that's that. So this is spatial. Li0 is pi hat square root of gamma squared minus 1. And L00 is just simply gamma. So that's the standard, that's L of P explicitly. Now, we can write this thing conveniently in the following way. R of P hat, a boost of P. And when I say P, I really mean P0. Or maybe I should, I'm going to write the 0 once, but in general, I'm just going to talk about P. Okay, R inverse of P hat. Now notice there's something arbitrary about this last term. Because L of P, what does this do to K? Well, it's R of P hat, B of P, R inverse of P hat on K. But K, for the massive case, is M 0, 0, 0. So the rotation operator has no effect. It's there simply for later reasons that I've forgotten about, but it's an intrinsic arbitrariness, and we're going to make it definite by putting it there. So this is actually R of P hat, B of P on K. Now what does B of P do? B of P takes K, which is a particle at rest, and shoots it off in, let us say, the Z direction. And so now it has full momentum P0, 0, 0, P, P3, say. So energy, momentum in the 3 direction. Or equivalently, it's R of P hat, E of P, 0, 0, length of P. All right, P is length of P. There. Now, what does R of P do? R of P takes the Z hat vector takes the unit vector in the Z direction to be a unit vector in the P direction. And so what do we get? What we get finally is E of P and then the vector P. So R leaves the 0 component invariant, just rotates 3 vector into the vector P.
That's a 3 vector P though, right?
This is 3 vector P. Arrow is 3 vector.
Why can we get rid of the R inverse? I missed this.
Why what?
So you in the second last line you have BP R inverse P K and you go
I
down.
still don't understand. Well, let me
Sorry. So in the second to last line you have like RP, BP, R inverse PK, and then you go down a line and the R inverse goes away? I missed why that goes away.
All right, great question. It goes away because this is a rotation and the fiducial vector has no space components.
Okay, yeah.
It's a particle at rest. You do a rotation, the particle at rest just says the hell with that. Or to put it differently, where actually I misspoke. This RP only acts on the 4 vector of the particle at rest. It doesn't act on the spin. Okay, this boost vector, by the way, this B of P, if you want to see what it is, it's 1, 1, gamma, root, gamma squared minus 1, root, gamma squared minus 1, gamma, 0, 0, okay. All right, before I do the next thing, let me erase the boards with some, and while they dry, I'll do the next thing. So what I've done so far today, I've been following Weinberg rather closely. But I think I'm going to be describing the Massless case more simply than he did. He is able to see so deeply into things that sometimes his explanations are
Yeah.
more complicated than necessary. Is
So
that a question there?
Yeah, I have a question about this BFP. So I think that this gets
About
back
what?
to about this BFP. So this kind of gets back to the question that Sam was asking. So I remember whenever we came up with whenever we were sort of, I guess we were like deriving a representation of the Lorentz group, we had these like generators that
I
were
had
always-
things called R and B.
and things called R and B, and the B things were the things that generally.
Oh, this B is
right?
totally different from my B's.
Okay.
This is B for boost, and it's a 4x4 Lorentz matrix. My B's were the generators of the Lorentz group. They're totally different.
Okay.
So what is that mean?
Okay.
And so
They
in
generate-
fact, I'm going to be talking about those B's in a moment. That and IB I called K.
Mhm. Yeah, so those B's aren't necessarily just the generators of boosts.
My B's are the generators of boosts. This B is simply a Lorentz boost operator. In fact,
So they're generators, you exponentiate them in order to get the.
yeah. In fact, what would have been a better notate? Well, you see, Weinberg, when he wrote his book, and I just followed it today,
Yeah.
he didn't know that I would be using B for boost generators,
Sure.
and he certainly didn't care.
Yeah.
So another way of writing this would be L sub B of P0.
Yeah.
And this would be L sub B of P0. And so this thing is again L sub B of P. So this just takes K into this thing here, P0, 0, 0, P3
Yeah. Mhm.
of the massive case.
Mhm.
But K has no component in last. K has no component in the last three coordinates.
K, right, K, for the massive case, K is M 0, 0, 0. Massive case. And actually, now that I think about it, unfortunately, I've been using for my vectors one notation. I just copied this out of Weinberg this afternoon to translate to my notation from his notation.
Wouldn't you just change?
Yeah, I mean, he's got, this is 1, 2, 3, 0. Okay, so in other words, I should have written it the other way because I was putting zeros on top. So I guess, let's see if L of B is actually simply that. But see, it may be that we need to switch the rows as well as the columns as well as the rows. Anyway, it is. My suspicion is that it looks like this. In fact, let me do it this way. I bet it's this.
Your 0, 3 component should be nice. Yeah.
But now this is a boost in the one direction rather than the three direction.
Yeah, okay.
So to go to the three direction, I guess what we do is we do gamma I'm guessing, but I mean, this is just off the top of my head. And this takes, this is probably right though, because it takes, this LB then takes K, which is M0, into gamma M 0, 0, M square root of gamma squared minus 1. So this is the energy, this is the momentum, and I think this actually satisfies the correct relation. So this is right. Okay, we have 10 minutes for me to try to do the next topic. Okay, unfortunately, the next topic is kind of dull. I really want to tell you about what follows the next topic. Because actually I only worked it out this afternoon. Previously I was just using Weinberg's way of doing things, which is not helpful. Let me see. Okay, what I'm going to do is I'm going to jump to what I think is interesting, and on Thursday I'll come back to this point. So let's now jump to the massless case, because it's kind of amusing. Okay, so what's the massless case? Well, the fiducial vector K is 1, 1, 0, 0. Weinberg's is 1, 0, 0, 1. And for that reason, I think for that reason he embarked on a rather complicated argument. And because of the stuff I did last week about the B's and the R's, what do we want? We want, what is the little group? The little group is the group of Lorentz transformations that leave this vector invariant. So let's look at the 6 generators and find out what they do to this 4 vector, and that'll tell us what's going on. Okay. So if you remember what the generators are, they are there are 3 R's and 3 B's, and what you can see is that R1 on K is in fact 0. Why is that? Because R1 is a rotation about the x-axis, and this is a vector. This is a vector in. This is a photon moving in the x direction. So x, y, z. The photon's going this way. Yeah.
I just a question about the little group. It's different if we're considering massless particle versus.
Yeah, it's
okay.
completely different. The little group is the rotation group in the massive case, and it's something else in the massless case.
Okay.
So if you have a rotation about the x-axis, obviously it leaves that 4-vector invariant, so the generator annihilates it. R2K, on the other hand, if you just multiply it out, R2 looks like this: 0, 1, 0, minus 1, all zeros, 1, 1, 0, 0. Well, this is 0, 0, 0, minus 1. R3 on K, well, this one has 0, minus 1, 1, 0, and everything else 0. Acting on 1, 1, 0, 0, what we get is 0, 0, 1, 0. Now, what about B's? Well, B1 on K, turns out this is just K, because this is 0, 1, 1, 0, 1, 1, 0, 0, and this is just 1, 1, 0, 0. So this is K. So B1K is K. On the other hand, B2K is 0, 0, 0, 0, 1, 1 on 1, 1, 0, 0. And this is 0, 0, 0, no, hold on, 0, 0, 1. Where is the eraser? Oh, here. And B3 on K is 1, 1, everything else 0 on 1, 1. And this is, so this is what happens, what the generators do to the fiducial vector in the massless case. So what we have is, okay, now let's figure out then what's going on. What are the possible, let's see, what do I want to say here? So what can form the Lie algebra of what combinations of the 6 generators of the Lorentz group can be generators of the little group for the massless case? Well, one of them obviously is R1. Rotations about, because they annihilate K. On the other hand, we see here that B3 plus R2 also annihilates K. So this can be a generator of the little group. And furthermore, B2 minus R3 annihilates K. So we have 3 generators of the little group: R1, B2 plus R2, and B3 plus R2, and B2 minus R3. And this is a group that Weinberg, of course, says the reader will immediately recognize that these are the generators of such and such, although he doesn't derive things simply the way I did. He derives them from some very deep argument, which I actually never understood fully, I don't think. So what are the commutation relations of these generators? Well, it turns out that B2 minus R3 commutes with B3 plus R2. You can check this. Because remember, we wrote down what the commutation relations were for all the generators last week. In fact, maybe I'll review some of this later. Moreover, B2 minus R3, commutator R1, in fact, is minus B3 plus R2. And B3 plus R2 commutator R1, that's a comma, is B2 minus R3. So these generators form a nice little Lie algebra. Little is a pun there, actually. Two of the generators commute, and those two generators have commutators with R1 that give them each other. Okay. And so that's rather nice. We could say let A equal B2 minus R3 and B equal B3 plus R2. So then we have the commutation relations that A commutes with B, and that A with R1 is minus B, and B with R1, there's a comma. B with R1 is A. So this is the Lie algebra of the little group of massless particles. And Weinberg has a name for it. Let me see what the name is. ISO2. So this is called the group ISO2. So that's the Lie algebra of a particular Lie group called ISO2. All right, so that's basically the end of we're at the end of the hour, but if you guys have questions, I can try to answer. Yeah.
I think I'm missing something, but these R2, R3 are rotations, right?
Yeah, all the R's are rotations.
So you're taking a vector that has energy, K has some energy 1, and it has a momentum in the x direction.
Oh, shit!
You're doing nothing but rotating it, say with R2, and you get something that only has a momentum. There's
Right,
something
if you
physical
rotate,
that I'm missing.
if you rotate K, oh, whoa,
It's a generator.
hold the
Okay,
phone,
okay.
hold the phone. R is a generator. Over there, R was an actual rotation matrix.
Right.
This is just a generator. The generator does that.
Okay.
That's a great question, though. Anything
I knew
else?
there was something simple I was missing, but.
Yeah, well, when we're lucky, it's something simple that you're missing. There are other cases that. All right, so now you may think that we've been going through an awful lot of stuff that's hopelessly abstruse and absurd and irrelevant, but in fact, it's just a short jump from where we are to full-blown field theory, because what he's done, what we've got so far is, and in fact, there's something about what I did at the end of the lecture today that's really somehow related to gauge theory in a way that I don't fully understand. And in fact, if any of you want to do a term project on this, I would encourage it. In fact, it's a little bit related to optics, and it has to do with massless particles, and the photons are an example. But anyway, on the other hand, if you want to work on something else, work on something else. All right, well, so if there are no more questions, all right, let's end it then.